My PhD work is focused on problems stemming from memory constraint settings. For instance, one line on my work concerns graph algorithms in models of parallel computation.
This is Slobodan Mitrović, a PhD candidate of the IC School at EPFL. Slobodan is working on efficient parallel algorithms to process data stemming from massive networks. Let's give examples of such networks.
Social graph or internet graphs. So we are talking here about graphs that have billions of edges, millions of nodes, and so it's really impossible to store them on one machine. Usually you have them on a farm of machines, and then you are making computation on them in parallel. But we are talking, let's say, about social graphs, which have even now billions of nodes, and they're just huge graphs. Another example, actually, which is used quite a lot in the practice, and MapReduce is used to build these kinds of graphs, is knowledge graph, which powers Google search. Right, these days is based on knowledge graph, and this graph also has a couple of hundreds of millions facts, and then lots of edges between them that model relations between the facts. You're really talking about billions of edges in the graph.
It's important to note that these days much of the big data on the internet is more or less of a graph. Typically, as Slobodan explained it, Google's representation of common facts is done through a so-called knowledge graph, and in this graph
each node is a fact, exactly, yes, and there is an edge between two facts if there is a relation between them, like EPFL and Lausanne. There will be an edge between these two facts stating that actually EPFL is in Lausanne. And then you build such type of graph on the facts.
But unlike basic graphs, the edges of the knowledge graph carry a lot of information.
There is more data on the edge. There is more data on the edge that tells you in what context these two facts are related, and also some statistics, how often they appear, and some quality, and so on and so forth. So it really has lots of information on every edge that fully describes that connection. It's essentially weighted graph with some additional attributes on every edge.
So the main point here is that graphs have become a major data structure, and they carry a lot of interesting information. The trouble, though, is that today's graphs are huge, and this makes their processing difficult.
Usually in these models, you're given machines that have certain memory, and you cannot fit, in case of graphs, for instance, you cannot fit the whole graph on one machine. So one of the main questions is, how do you partition your graph across several machines so that the output, the structure that you can design on each of the machines independently can give you sufficient information of how to design the whole structure. So if you think of matching, of finding maximal matching in the graph, you want to partition your graph in disjoint pieces, and on each of the pieces find some matching, but then overall, when you take union of those matchings, you get something which is large matching in the original graph. And you're allowed to repeat this process a couple of times, but the goal here is to actually repeat this process as few times as possible. So this is somehow the main challenge, right? How do you partition the data so that you can get efficient progress, and how you can obtain the final result in a small number of computation rounds? Because computation here is the main bottleneck. Yeah. Usually you exchange lots of data, and you want to reduce that.
But what kind of information may we want to retrieve from such big graphs? Early on, Slobodan discussed matching, which is a classic problem of computer science, and which is typically one that needs to be solved by Amazon, Airbnb, or Uber, in which buyers and sellers must be correctly matched. Another problem is
maximum independent set. It's also one of the problems I was looking at. So it's used, for instance, it has some applications in finding dominant nodes in the graph. It's very related to in some sense, to this problem also vertex covers. So what is your goal? You have, let's say, social network, and you want to find a relatively small number of nodes, so that when you take those nodes, they would cover most of the social graph. Think that you have a product that you want to distribute to some users in your social networks. and you hope that if you give them for free, they will advertise on their feed, or their news feed, that they got the product for free, and then their friends will actually see the product on their news feed. In that case, you want to find some small set of nodes that kind of dominate the whole graph. And in this kind of scenarios, vertex cover, maximum dependent set, they have some applications.
Now, Slobodan has proposed new algorithms to process massive graphs in a parallel manner, and they are pretty impressive.
For instance, if you have a graph that consists of 1 billion nodes, you need roughly up to some small constant factors. You need roughly 5 or 6 rounds to find maximum independent set on such a huge graph. So you need only 5 or 6, again up to maybe some small constant factors, but that's roughly the number, 5 or 6 communication rounds to find maximum independent set on such a big graph.
Okay.
Which is
very nice.
and you can think that on every graph you can store like very rich, lots of information that you can store up to 10,000 or 100,000 nodes. So it's much smaller than the whole graph, but still you need only small number of rounds to actually find maximum dependent set.
And yet this is without prior assumptions on the structure of the graph.
This is for every graph. If graph is sparse, then you can do it even faster. This is when graph has lots of edges, but if it's sparse, then you can actually do something faster.
What you would have in the center is the most famous characters. For instance, here you would have the Emperor, so the Palpatine. Here you would have Luke Skywalker, and this blue Yoda, and all the famous characters.
And to have everything running efficiently, very quickly, right, and preferably in real time, you need some recovery algorithms that are efficient.